Today's lesson is lenses. So, lens is an optical device like this. So, if you see this, you have curved surface made up of glass, plastic, or any other transparent material. So, in this, what happens when a light ray passes through this lens? It alters the direction of the light ray so that the light ray gets refracted and it will change its path, right? Lenses are used in telescopes, binoculars, microscopes, magnifying glasses that we also call as simple microscopes. Likewise, in many optical instruments we use lenses. There are various types of lenses. The lens with two convex surfaces, the lens with two convex surfaces are called as biconvex lens. The lens with one convex surface and a plane surface is called as planar convex lens. The other one has two concave surfaces, so it is called as biconcave lens. So the fourth one is the one with a concave surface and a plane surface, which is also known as planar concave lens. So these are the four types of lenses that are used in normal day-to-day life. Mainly we use biconvex and biconcave lens in optical instruments. Let's move on to convex lenses. So when a convex lens is taken, you can draw two imaginary spheres on either sides of the lens. So if you see this, you can see if this is the lens, right? You can form two imaginary spheres from this convex surface, right? So this is the center of this sphere and this is the center of the second sphere, right? So if we draw an imaginary line in between these two, joining these two, I will name this as C2 as a center 2. I will name this as C1, right? So the radius of C1 is equal to radius of C2, and if you divide this distance C1 C2 distance, you will meet a point. We also call it as the optical center, right? So this optical center is the place in which light rays don't get refracted. So if a light ray passes through this optical center, it won't be refracted in either ways, right? So let's take a lens like this. If this is the optical center, any light ray that passes through the optical center won't be refracted, right? It can be either ways. It can be anything like this. Even though lenses refract light rays, the optical center is the place in which light rays would not be get refracted. This line which we got by joining C1 and C2 is called as the principal axis of a lens, right? So the C1 C2 line, we call this as the principal axis. The line joining C1 C2, this whole thing is called as the principal axis. If I take a lens like this, a bigger one, so that I can show you how light rays get refracted. So let's say if this is the optical center and the line passing through this is called as the principal axis, right? So if a light ray that comes like this hits the surface, what will happen? If you draw the normal like this light ray will be refracted. So as you can remember in the previous lesson, in refraction of light, when light enters from air to glass, what will happen? Air is rare, glass is denser, so rare to denser, the light ray will be refracted towards the normal. So this will be refracted like this, and if you draw another normal here, right, denser to rare will be bent away from the normal. It will be like this, right? So this is how a light ray gets refracted in a lens, right? If I draw you another one from top, same thing happens. If I draw you the normal, it will refract towards the normal. And if I draw another normal here, right, this will be refracted away from the normal. So this was the path that was going to be, it will be refracted towards it, right? So there is a particular point here on principal axis in which every light ray gets refracted. So this point is called as the focal point, right? So if any light ray which comes parallel to the principal axis will get refracted, will move through this focal point. The distance between the lens and this focal point is known as the focal length. The distance between the lens and this focal point is called as the focal length. Normally, focal length of a convex lens can be determined roughly by using it to focus a distance object to a screen, right? Let's say you have a tree here, right? Let's say this distance is very large compared to this distance, right? If you keep a screen like this, you can obtain an image of this tree on this screen. Here you will be obtaining an image of this distance tree. So to obtain this image, first of all you have to do is you have to keep the lens, you have to direct these light rays into the lens, and you have to change this distance and check whether which distance gives you the clear image of this tree. So that distance will be the focal length. Symbolize it as simple f. Okay, let's move on to drawing ray diagrams. So when drawing ray diagrams, there are mainly three things that you should know. Number one is the light ray that passes through this optical center or optic center will move without getting any refractions. So it will be like this. So any light ray that passes through the optical center will not get refracted. Number two is when a light ray comes parallel to the principal axis, it will be refracted so as the ray goes through the focal point. Number three is the opposite of second one, that is, if the light ray passes through the focal point towards the lens, what will happen? It will move parallel to the principal axis. So here, when the light ray comes parallel, it will move through the focal point. Here, when light ray comes through the focal point to the lens, it will be refracted so that the principal axis and the refracted light ray are parallel to each other. So there are few points that you should know. As you can remember earlier, in earlier diagram, I drawed you two spheres. If this is the center and if this is the optic center, the distance or the midpoint in between these 2 points will give you the focal point, right? So if this is the center of the curvature and if this is the optic center, the midpoint of these two will give you focal point. So focal point lies on either sides of the lens, as the sphere also contains center of curvature. So the midpoint between optic center and center of curvature will be the focal point. Let's see the images found by convex lenses. In convex lenses, when the distance between object and the lens differs, the size, the shape, the nature of the image will also change. Let's take a look at it. I'll take number 1 as when the object is between the lens and its focal point. As you can see here, the light rays that are coming from tip of the arrow doesn't meet after they get refracted. So the images formed like this cannot be taken onto a screen. That is because the light rays won't meet at the point. But if you draw backwards, you can see these two light rays will meet behind the lens, so that we can see through the lens a virtual magnified upright image. So this image will be always larger than the object, and the position of the image is greater than the object distance on the same side as that of the object. If you keep an object on the focal point, you can see the light rays will meet at infinity. So the position of the image will be at infinity. So the nature of the image formed on infinity cannot be stated clearly. But we say generally, if these two light rays meet at infinity, the image formed will be always larger than the object, and it will be inverted, and also it will be real. So let's move on to the third position, that is when the object is kept greater than the focal length and less than twice of the focal length. So if you see this diagram, you can see position of the image lies in a place where it is greater than twice of the focal length on the opposite side. And if you see this image, it is upside down. This kinds of image where this image is upside down than that of the object are known as inverted image, right? So that as you can see, these light rays meet actually, the image form will be a real image, meaning that this image can be taken onto a screen. So this image will be also larger than the object. If you move on to fourth position, that is if the object is kept at the twice of the focal length, or we call it center of curvature, we can see the image will lie on twice of the focal length on the opposite side, and it will be real image, and it will be an inverted image as you can see it here. So if you see the size of the image, it will be the same size as that of the object. So this is the only place in this convex lenses where you can obtain the image as same size as that of the object. Let's move on to fifth position, that is greater than twice of the focal length. So as you can see it in the diagram, the position of the image will be greater than the focal length and less than twice of the focal length on the opposite side. And as you can see, the light rays meet, it forms a real image and it is inverted. So always these kinds of image, or the image formed when the object is kept at a distance greater than twice the focal length, is always smaller than the object. Let's move on to sixth position. If you think an object which is kept at infinity, the light rays that travel from infinity gets refracted by the lens, the image will be forming on the focal point of the other side. So as you can see, the light rays meet, we say it as a real image, and also it is inverted. If you can remember the experiment we did earlier to get the focal length, the same thing happens here. Like this, the object was the tree, so the image will be always smaller than the object. So here also, when light rays that are coming from infinity will be refracted, so that the image will form that focal point and the image will be always smaller than the object, as in the experiment. Let's move on to concave lenses. So here also, when you take the concave lenses, you have two concave surfaces. So here, like the previous example, if you draw imaginary spheres from these surfaces, you can get center of the sphere, let's say C1. You can get center of the sphere also as C2. As in convex lens, here also you can join these C1 and C2 to form the principal axis. And if you consider the midpoint of C1 and C2 distance will be the optical center. So this point is called as the optical center. And if you take the midpoint of optical center and the center of curvature or center of sphere, you will get the focal point. Here also, the midpoint of optical center and center of sphere will give you the focal point. If you consider the light ray that comes parallel to the concave lens, hits the concave lens, what happens? These rays will be diverged, right? In convex lens, what happened? The rays that are coming parallel was converged to the focal point. But here, what happens? The light rays will be diverged as it is coming from the focal point which is behind the lens. When you take another light ray which is parallel, this light ray will be also deflected so as it is coming from this point. So we draw it as dotted lines, and then if you extend this line, you will get the light ray. As in convex lenses, in this lens also, the light rays which moves through the optical center will not get any refractions. Let's see how a ray diagram is drawn in concave lens. So these are the two focal points, and let's say this is the object we are considering, right? So we always take light rays that are coming from this tip of the arrowhead. Let's draw a parallel line that is coming to the concave lens. So this light ray will be deflated as it is coming from this focal point. If you draw another ray through the optical center, you will notify that, as I said it earlier, the light rays which are traveling through the optical center won't get any refractions. So as these two light rays doesn't meet, it will not form a real image. But if you consider these dotted lines, you can see this light ray and this light ray meet at this point. So that it will form an image here. We call it as I. So that if you see the nature of this image, this will be always smaller than the object and it will be upright and virtual. So unlike convex lenses, in concave lens, wherever the object you keep, you will always obtain an image like this. An image which is smaller than the object, virtual and upright image. So these virtual images can be seen if you keep the eye at this point. Let's see how hand lens gives us the enlarged magnified virtual image. So hand lens contains a convex lens, right? So if this is the principal axis, let's say you have focal points at equidistance from the lens. Let's say you are reading a newspaper, right? You are reading a newspaper and you are keeping the hand lens near the newspaper, so that what you are doing is you are keeping the object in between focal point and the lens. So let's say this is the object, I mark it as O, and if you mark the light rays, let's say we always take a light ray which is going parallel to the lens and it will be refracted through the focal point. Let's take another ray which is going through the optical center like this. So these two light rays will not meet. So what we are doing is you are extending these light rays backwards. So if we extend these light rays, you will see that an image is formed here, that is larger than the object, virtual image. So when you keep the lens like this, what happens? The letters will become magnified. So this is what happens in a hand lens. There are few points that you should know. One is, when lenses form real images, the image will always be inverted. If the lens form an virtual image, it will always be an upright image. Also, if you consider reversibility of light, the reversibility of light is like this. As you can see here, I have a prism, a convex lens and a mirror, right? So if I send a light ray perpendicular to this prism, what will happen? As you learn it earlier in refraction of light, it will get totally internally reflected and it will move like this, right? So when it passes through the convex lens, it will get reflected like this. So what happens here is the mirror reflects this light ray back, so that this will follow the same exact path where it came. If the direction of the light ray is reverse, it will follow the same exact path backward. This is what you call the principle of reversibility of light. Here are some ray diagrams of images formed by microscope and telescope.